So the idea is this: it is exactly, we cut a piece of the region into many pieces, right? Then we evaluate each one as a rectangle. Then we say, okay, let n run to infinity. So which means cut the region into infinite many pieces. Riemann sum R is called Riemann sum because of this. Okay, because Riemann is a great mathematician. He's a German mathematician. All right, so this is a super important idea. All right. So this definition of a definite integral, all right, definite integral. If f is a function defined on a closed interval from a to b, okay, closed interval including a, including b, the definite integral of f from a to b is a number of this. Okay, this is defined as what? This is defined as this. All right, what is this? This is to say, from a to b, let's say we have, this is our coordinates. Let's say maybe this is the value a. I'm going to only work with the first quadrant for now. Okay, of course a can be negative. Let's say this is a, this is a b, right? We're treating f as a function. So treating f as a function. So we want to find the area of this. The area of this shaded region. Right? So this is a, the lower part is a, this part is b. And what do? We cut this into n pieces, many pieces, right? We approximate with a rectangle. Then we let this, let's say we cut into n pieces. Then we let this n goes to infinity. Or we say this, we cut into, so let's say this is one of the piece, and we call this delta xi in this case. Delta xi. Okay, before we call it 1 over n. So here we cut into many pieces. We cut into many pieces, and each piece, the width, we call changing in x. Right? So we use this, we call this delta xi. That's a symbol. So this means changing in x. Or this equals to b minus a divided by n. All right, so here. Well, you can look at this as 1 over n. All right, this is one, not 1 over n, because now we're working with the interval a to b. So this is b minus a divided by n. I think we have some way in the first part, maybe. Oh, right here. Okay, that's the definition of this delta x. Delta x is b minus a divided by n, which means changing in x. All right, changing in x. So each piece, the width is delta x. All right, delta xi. This one, delta xi, delta xi, delta xi. Then multiply by the height. The height depends on the chosen point, right? We can approximate on the left point, we can approximate the right point, we can approximate in the middle point. So this x star means the chosen point to evaluate the function value f. So the idea is still the same, right? We sum up all the areas of the rectangles. So sum up n pieces of rectangles, the area of rectangles. Then we let the changing of x goes to 0, which means 1 over n goes to 0, which is the same to say cutting into infinite many pieces, right? It's the same thing. If we write this as 1 over n, and then this limit let n goes to infinity, it's the same notation, just the notation changed a little bit, right? So this is a finite. So this delta xi means this 1 over n before, changing in x. So let changing in x goes to 0. Okay, cut into infinite many pieces. And we define this whole thing as this, as the integral. So this is the finite sum, and we defined as this, the elongated s. So, you're writing the integral sign as s, long s, all right? Then from a to b, all right, from a to b, so this lower, we call this lower limit. A we call lower limit. B we call upper limit. Okay, so integral with the lower limit a, upper limit b. F of x dx. You see, we change this delta xi into dx. So dx and this integral sign is a pair. Is a pair. We cannot write one without the other, all right, in this case. So what does this mean? What does this notation mean? This integral sign from a to b dx is a pair. Means we're cutting from a to b infinite many pieces. So we always write these two in a pair, okay? Integral sign and a dx is a pair. If we only write one, that does not make sense, all right? So write the integral sign with dx. Because we have a lower limit a, we have upper limit b, we call this a definite integral. Without the a and b, it's not a definite integral, okay? With lower limit, with upper limit, we call definite integral. Okay, so this is definition. This is new. Let me make sure you understand this definition. This is from a finite world. By taking limits, while we go from finite world to infinite world. Then we call this whole thing integral from a to b f of x dx. Okay, this is integral. Integral with this elongated s with a lower limit, upper limit, and a dx. In the middle, the function in the middle is someone's derivative. All right. So f of x is someone's derivative function. You can think as capital letter F prime. Okay, let's see this theorem. If f is continuous on the closed interval, or if f has only a finite number of jump discontinuities, then f is integrable on AB. That is, the definite integral of this exists. Okay, this is very mathematical. This is saying from A to B, right? The function can be continuous, or function can have a single, function can discontinue at a single point. At this point, because what is the area at a single point? There's one dimension, which has no area. So that's why the theorem is true. Okay, let's see this one. So this is a better one. This is better than before. If f is integrable on AB, then the integral with lower limit a, upper limit b, f of x dx equals to limit of this finite sum, right? xi is the chosen point to evaluate the function value. Delta x, the change in x. Then we add all the area, we multiply those two dimensions, get an area for the rectangle. we add up n rectangles. Then we let n rectangles to be infinite many rectangles. And that's defined to be this, the integral of this definite integral. And what is the delta x? Delta x is b minus a, right? The upper limit minus the lower limit divided by n. So which means we're cutting from a to b as for n pieces. Let's see this one. Express limit n goes to infinity of this sum of rectangle area of rectangles as an integral on the interval 0 pi. Well, we're just writing this, this is from 0 to pi. So our lower limit is 0, our upper limit is pi, writing as the integral sign, x cubed plus x times sine x dx, right? So basically we're writing, it's like a limit is like a bridge, all right? Limit is a bridge. You build a bridge from finite world to infinite world. Yeah, that's it. Just make sure you understand, what's behind this definition, this theorem. The function can go above x-axis, can go down x-axis, can go above x-axis. Then what is the area? The area would be above x-axis will be positive, down below x-axis will be negative, okay, when we evaluate. But that's okay. So this is pure mathematical, okay? This is pure mathematical. So that's why we have negative area. For now, don't worry about that. When we talk about applications, we will worry about that. But at this moment, it's only pure mathematical. So we have negative area. Okay. Let's see this example. Example 2. Evaluate the Riemann sum for f of x, x cubed minus 6x. So this is a function. Taking the sample point to be the right endpoint. So we take the sample point to be right. So we evaluate the function at the right endpoint. And a equals 0, b equals 3, and n equals 6. So b, we evaluate this integral with lower limit 0, upper limit 3 of the function dx. So n equals 6. So we have delta x equals b minus a divided by n. 3 minus 0 divided by 6, which is half. So this is, remember before we call 1/n. Okay, so 1 over 2. So each width, so this is the function. And we cut it into 6 pieces. So 1, 2, 3, 4, 5, 6. So we cut it into 6 pieces. And each one, the width, so this is notation delta x. The width of each rectangle is half. So all we have to do is find the function value at the right point, right? We want to find the function value here, the function value here, the function value here, the function value here. Because we evaluate, we choose the right endpoint as for our evaluation, right? So we just plug into those x values. The first one will be half, right? So f of a half. The second one would be half plus half would be 1, f of 1. Then f of 1.5, f of 2, f of 2.5, f of 3. Then multiply by delta x, changing x, which is half. So half times all those. Add up, we get negative 3.93 something. So why we get negative? Because the area down below is more than the area above. So have this pure mathematic area. Now, let's see B. B says evaluate this. So let's use the definition. The definition is saying f of xi delta x, let n run to infinity. Then f of xi, let's just plug in, right? Plug in, what do we get? We get f of 3i divided by n. So we have to do a little bit of calculation. So in general, xi equals 3i divided by n, because we're cutting into n pieces, right? Then multiply by 3 over n. Because we're cutting 6, what do we have? We have 3 minus 0. So b is 3, a is 0, 3 minus 0, which is 3, 3 divided by n. So in general, cutting into n pieces, 3 divided by n. So the width of each rectangle is 3 raised by n. Then the first one, we're evaluating at the right point. The first one would be 1 of 3 over n, 2, of 3 over, and so on and so forth. So we evaluate the function value, then we do the calculation. In the end, to get a limit when n approaches infinity. We have this. So then let's see. So 81 times 4, 1 plus 1 over n squared minus 27 of 1 plus 1 over n. If we simplify this, we take a limit. So 1 over n squared, because when n goes to infinity, remember what does 1 over n go? 1 over n goes to 0. 1 over n goes to 0. So then we'll have 1 left, 1 times this, 1 times this. So I have 81 over 4 minus 27. Simplify, we get negative 6.75. Comparing those two answers, there you get negative 3. A very big approximation, very rough approximation. So this is precise. So this value is precise value. All right. So the area from here to here, which means the area of the bottom minus the area of the top, is this much. It's precise. Here we have other two examples. Okay, the first one is saying evaluate this, the definite integral from 0 to 1 square root of 1 minus x squared dx. The second one is from 0 to 3 x minus 1 dx. So let's see the first one. The first one, let's look at this function, right? Square root of 1 over x squared equals f of x. And from that's a circle, right? Think of f of x equal to square root of 1 minus x squared. Right? We see a circle with square both sides. We have y squared equals 1 minus x squared. Move negative x squared to the other side. We have x squared plus y squared equals to 1. So it's a unit circle, right? Unit circle. So the function inside it's part of unit circle. Then the limit is saying going from 0 to 1. So a is 0, b is 1. So 0 to 1. So that's the quarter circle in the first quadrant. So this whole thing represents the area of quarter circle in quarter circle. Of course, we know the quarter circle, right? Because we know that's quarter of unit circle, which is pi over 4. Let's see B. So B, if we read it, we have f of x equals x minus 1. That's a line, right? That's a line. It's a straight line. You can draw the line. And then it says go evaluate from 0 to 3. Evaluate from 0 to 3. From 0 to 3, we see two rectangles. One small rectangle down below x-axis, one rectangle above x-axis. So area of this is negative half. Area of this, well, the y value is 3. 3 times, y value is 2. 3 minus 1, which is 2. 2 times 2 divided by 2, which is 2, right? So I have 2 minus half, which is 3 halves, 1.5. But this is just typical examples, all right? Special examples, let's put that way. Those are the special examples. What if we have this, we call this integrand, all right? This inside the derivative. So this is someone's derivative, we call integrand. It has a name. Integrand. Integrand. You know what? I forgot how to write it. Let me just make sure of the spelling. For now, just remember it's integrand. I think it's integrand. No, not the integral. Integrand. Oh, okay. You give me a good hint. Integrand. I think I'm not quite sure if written this way. So the inside the derivative function is called integrand. Okay, if this is wrong, I'll change it. But for now, just remember the pronunciation, integrand. So sometimes the integrand will not be this nice. Okay, sometimes okay, maybe you're right, integrand, I-N-T-E, integrand. I don't know why it doesn't look so good to me. Oh, okay, integrand. So sometimes this integrand we may not do, these things. We may not be able to analyze this way or this way. And so what do? We will use antiderivative because we know the integrand is always someone's derivative. So we want to use antiderivative skill. This is still use middle point to approximate. So this one is saying if we switch the upper limit and lower limit, then introduce a negative sign. At one point, so A to A, at one point, the area is 0, okay? Because at one point, we just have this height, we have no width. This is one dimension. For one dimension, we agree the area is 0. The properties for limits stays true for integrals because the integrals is infinite, in the end, is just a limit. We can factor out the scale. If the integrand is a constant function, we can factor out outside, or that's just equal to c times minus a. If the integrand is the sum of two functions, we can split it into two integrals. If c is a scalar inside the integral, we can factor out the integral. In a subtraction of two functions, if the integrand is a subtraction of two functions, integral becomes a subtraction of two integrals. Okay, this is example, right? So the integrand is the sum of two functions. It's 4 plus 3x squared. So we can split it into sum of two integrals. Then we evaluate this. This is a 4. 4 is constant. So I have 4 times 1 minus 0. 4 times 1 minus 0, which is a 4. And this one is x squared, which from before we evaluated is 1/3. So 3 times 1/3, that's 1. 4 plus 1, that's 5. So this basically is saying, okay, adding the integrand is adding two functions. The integral is just adding the two integral. We can split them. And also, if C is in the middle of A and B, just like this picture, the C is in the middle of A and B, the integral from A to B, we can split into the integral from A to C and C to B. So A to B, we can split into A to C, C to B. C is a number in between of A and B. Because the area at C is 0. That's why we could do that. So this is using the property. This is if it's known from 0 to 10, the integral is 17. The integral function is 17. And also known from 0 to a, the integral is 12. Then we will know the integral from a to 10. Just subtract those two, we get 5. So if function is always non-negative, and for x in between a and b, the integral from a and b is always positive, always non-negative. For two functions, if one is always greater or equal than the other one, and for all the x value in between a and b, the integral always bigger than the other one, which is obvious, right? If you think about the rectangles. If a function is bounded between two values, then the integral is also bounded. Okay, we can use the property to estimate this. Square root of x from 1 to x. The function is the square root of x. And from 1 to 4. So 1 to 4. So f of 1 equals to 1. F of 4 equals to 2. Right? So this is saying the integral is also bounded in between of 1 times 4 minus 1 and 2 times 4 minus 1. That means it's bounded. If a function is bounded, if the integrand is bounded, the integral in the interval is also bounded. Excuse me. Let me choose. Let's see. Express the integral as the limit of Riemann sum. Okay, let's try a couple of them. Let's try those 3. Use the definition. Apply the definition. All right. 19, 21, 23. We'll spend maybe 10 minutes. Try this. Try 19, 21, 23. Okay, so we have 19, 21, and maybe someone can do 23. All right, 2 more minutes. I'm missing so many people. Okay, let's start. So we start with 19, Amir 19, then Raphael 21. Hopefully someone can show 23. Amir, are you talking? I cannot hear you.
Oh, sorry, Professor. So we're given 5 to 4 minus 2x, and we're told to find the definite integral. So what I knew is that this right here is the same thing as the antiderivative evaluated at b, which is 5, minus the antiderivative of value at a, which is 2. So I use the capital F here, right here. So first what we need to do is find the antiderivative of this. So if we do that, we get 4 times x to the first over 1, that's 4x. And then we have here negative 2 times x squared over 2, that's negative x squared. And then all we do from here is evaluate this at 5 and 2. So for 5, we have here 20 minus 25, that's negative 5. And then for f of 2, we have here 8 minus 4, that's 4. So negative 5 minus 4, that would equal negative 9. That's our solution.
Right, Amir is ahead of us. So we will talk about this later. There's a theorem called, a very important theorem, called the fundamental theorem of calculus. So he's applying that. So we will talk about that. So the integrand, all we have to do is to antiderivative the integrand. When we antiderivative the integrand, we got a 4x. If we think whose derivative is 4, that's 4x. Whose derivative is negative 2x, that's negative x squared. So we antiderivative. Then after we antiderivative, all we have to do is to evaluate this big F. Right? We're thinking this is derivative of F. This is the original F. So we calculate the original F. So we're treating this as F prime. All right, so the integrand is someone's derivative. Let's say this F prime. So antiderivative, we call this F. Then we evaluate at 5, the upper limit. Then we evaluate at the lower limit, F of 2. Then we subtract. Right? That's right, the fundamental theorem of calculus. You think it's called a fundamental theorem, so it's super important. We will talk about that too. Okay. Thank you, Amir. Raphael?
Yes, hi. So share my screen real quick. Hello. Okay. Got it? All right. So we start out with upper bound of 10 and lower bound of -2. And basically asking us, to find the antiderivative of x squared plus x. And we know our variable of integration is x, obviously. Equals, and then we applied, the power rule. So, n plus 1 as exponent divided by x plus 1. So x cubed divided by 3, and then plus that will carry over. So and since there's a 1 here, n plus 1 is 2 divided by 2, 1/3 x squared, cubed, plus 1/2 x squared. And then it's basically, as we were talking about, to evaluate at 10 and then subtract at -2 for this antiderivative. So you get 1/3 times 10 cubed plus 1/2 10 squared, and minus, and then I put this in brackets because we need to subtract that entire evaluation. So 1/3 times -2 cubed plus 1/2 -2. 1/2 -2 squared. Close bracket. And then once you evaluate that, right, because we need to distribute that negative over here to the -8/3 plus 2. So you actually, I just made my combining these two because they have the same denominator. So 1,000/3 plus 8/3 because negative distributed. And then plus 48 because you have +50, and then it's -2. So you get 1,008/3 plus 48, which actually is equivalent to 184.
All right, Raphael, you also use the fundamental theorem of calculus.
Yes.
All right, so let's go back a little bit. So let's see the question. The question is saying use the form of the definition of the integral given in the theorem 4 to evaluate the integral, right? So my purpose was for you to practice this with the theorem. Let's see, anyone wants to show 23?
Yeah, exactly what Amir was talking about.
Yeah, we will talk about the fundamental theorem of calculus later, but for now, we want to be able to understand where does this come from. So we want to be able to understand the definition. We want to be able to understand the theorem 4. Let's go back to theorem 4. Remember, the limit is a bridge up finite world and the infinite world. Theorem 4. Where's theorem 4? Right here. Right? So we want to use this. We want to use this to prove at this moment. Let's see what's our first one. So let's do here for our first one. So the first one is, so f of x equals to 4 minus 2x. We want to use this theorem. This theorem is saying take the limit, let n run to infinity, sum up all this. So what would we get? We would get, we have a b equals 5. Okay. So the upper limit and lower limit were given. So 2 to 5. So we have to use this. So what is our delta x? So we have 5 minus 2 divided by n, right? Which is 3 divided by, which is 3. So 3 divided by n. And we have f of this xi. But this xi is just 3 divided by n times I, or 3i divided by n. Right, multiply by 3 divided by n. But we want to use this. But in the end, it's the same as this. But at this moment, to practice that is to understand this, to understand where does this integral come from. All right, so I hope you take your time to do that. But now let's go into, since it seems like all of you know, most of you know the fundamental theorem of calculus already. Let's just talk about that. That's like a shortcut. All right, we don't really have to go through the definition. We don't really have to go through this heavy calculation because we have something called the fundamental theorem of calculus. Okay, so 4.3, evaluating definite integrals. Okay, since we have definite integral, which means we have lower limit, we have upper limit, and this, we want to use this evaluation theorem. This is saying if f is continuous on the interval of lower limit, upper limit, then, so here we're treating this f of x as the derivative of capital letter F. Okay, the derivative of capital letter F. Then that equals to f of b minus f of a. All right, so f is antiderivative of f prime. Antiderivative of f prime. And later on, this becomes the first part of fundamental theorem of calculus. So let's see this example. So the integrand is x squared. That is to say, capital letter F prime is x squared. So what is this antiderivative? That's 1/3. That's x cubed divided by 3, right? So antiderivative of x squared, that's 1/3 of x cubed. Then we evaluate at the top limit, upper limit. So f of 1, that would be 1/3 times 1 cubed. Then subtract evaluation of f at 0, the lower limit, f of 0. F of 0 is 1/3 times 0 cubed, which is 1/3. If we use for applications, if the integrand is velocity, right, from A to B, and the antiderivative of velocity is displacement, so that equals displacement evaluation at B minus displacement at A. Or let's see this one. Lower limit -2, upper limit 1, integrand is x cubed. So antiderivative of x cubed, we use power rule, right? Remember power rule? Antiderivative, add 1 to the exponent, divided by the new exponent. Add 1 to 3, we get 4, x raised by 4, divided by 4. So we get a quarter x raised by 4. Then we evaluate this function at 1, f of 1, subtract f of -2. So f of 1 is quarter times 1 raised by 4 minus quarter times -2 raised by 4. We evaluate, we get -15 over 4. Negative area only means the area and the x-axis is bigger than the area above x-axis. That's how we get negative value. Okay, this is saying find the area under the cosine curve from 0 to b. Right? Let's say b is in the middle of 0 to pi over 2. So cosine function goes this way, right? It's a symmetric over y with y-axis. From 0 to pi, cosine 0 is 1, cosine pi over 2 is 0. So we have this kind of a shape. And let's say b is somewhere in the middle, right? B is somewhere in the middle of 0 to pi over 2. We want to find the area of that area from 0 to b. So how do we do that? So we have lower limit 0, upper limit b, cos x dx. Right? So whose derivative is cosine x? Sine x. So antiderivative cosine, we get sine. Then we want to evaluate b, evaluate at 0. Usually give a long bar here, all right? So this indicates we're going to evaluate sine at b and sine at 0, subtract them. So sine b minus sine 0. Sine 0 is 0, so we get sine b. So we're using antiderivatives. So indefinite integrals. Indefinite means we do not have lower limit and upper limit. Definite means we have lower limit, we have upper limit. Indefinite means we do not have lower limit, we do not have upper limit. All right. So we want, and when we enter derivative of this, so this should be adding c. Okay. We add c to it. Remember when we enter derivative, right? We always add a constant term. We always add a constant term to the antiderivative. So we get a family of antiderivative functions. So if we do have a lower limit, upper limit, we can evaluate. We get a number. Okay, we get an area. If with indefinite integral, we get a family of functions. Right? So we do not have a lower limit, we do not have upper limit. We still can antiderivative this. So antiderivative of 1 over x squared is negative 1 over x. Then we add c. We add c to it. Antiderivative, so integral of secant square, that's tangent x plus c. Because the derivative of tangent x plus c is secant square. Okay, the same rules for limits. All right, so let's see this table of indefinite integrals. If it's a scalar inside the integrand, we can factor out the scalar for the integral. If it's constant, if the integrand is constant, we just get a kx plus c, because whose derivative is a number. That's just a number multiplied by x. The integral of sine x dx, that's negative cosine x plus c. Integral of secant squared, that's tangent x plus c. Integral of secant tangent, that's secant plus c. The integrand is a sum. We can split it into two sums for indefinite integral 2. If it's a polynomial, if the integrand is a polynomial, we use power rule. We add 1 to the exponent, we divide by the new exponent. Then add c. And n cannot be negative. If n is negative, that's log. Last time I add to the table. If the integrand is cosine, so integrate cosine, we get a sine plus c. Integral cosecant square, we get a negative cotangent plus c. Integral of cosecant cotangent, we get a negative cosecant plus c. Okay, let's see example 3. Find the general indefinite integral. Okay, we have 10, the integrand is 10 x raised by 4 minus 2 secant square x. So the first one we use the power rule, right? We add 1 to 4, we get 5, and then divided by 5, we get 2x raised by 5. We get 2x raised by 5. And the negative 2 we factor out, negative 2 factor out. And the secant square, antiderivative of secant square, we get tangent, so minus 2 tangent. Then add a constant term. Add a constant term. All right, if we differentiate this, we get back to our integrand. All right. Let's see this one. Evaluate 0 to 3 x cubed minus 6x. We did this one before, right, by using the definition and the theorem. Now let's just use this evaluation rule. So we antiderivative of x cubed, we get a quarter x raised by 4. Antiderivative negative 6x, we get negative 3x squared. Then we just evaluate at 3, evaluate at 0, subtract them. So quarter times 3 raised by 4 minus 3 times 3 squared minus quarter times 0 minus 3 times 0. So this term will become 0. We evaluate, we get negative 6.75. Remember before we use the definition, right? We use the definition and the theorem 4, we get exactly the same number, negative 6.75. Okay. So now we use the evaluation theorem. We get exactly the same answer. Because in the end, everything comes from, we remember the definition of derivative is the limit, right? Let's see this one. Find a definite integral from 0 to 12. The integral is x minus 12 sine x dx. So we just antiderivative each term. So antiderivative of x, that's x squared divided by 2. Negative 12 factor out. Antiderivative of sine x, that's negative cosine x. Then we evaluate at the upper limit, evaluate at the lower limit, subtract them. So we get 60 plus 12 cosine 12. Well, let's see this one. Lower limit 1, upper limit 9. The integrand is polynomial-like. So we want to simplify this polynomial-like, right? 2t squared divided by t squared, we get 2. T squared, square root of t squared becomes square root of t. Square root of t, you can write it as t raised by half. The minus 1 over t squared, we can write it as minus t raised by negative 2. So because it's a polynomial-like, we can apply polynomial rule for antiderivative. So antiderivative of 2, we get 2t. Antiderivative of t squared, we add 1 to half, then we divide it by half plus 1. Half plus 1 is 3 over 2. So we have t raised by 3 over 2 divided by 3 over 2 is the same as multiplied by 2 over 3. Minus t raised by negative 1, we add 1 to negative 2, we get negative 1, then divided by negative 1. Then we evaluate at the top limit, upper limit 9, subtract evaluation at the lower limit 1. So after calculation, we get this. Let's see this example. Example 7. This is how we use the idea in applications. A particle moves along a line so that its velocity at time t is this. So v of t equals t squared minus t minus 6. So measured in meters per second. So this is a quadratic function, right? So we know s of t will be 1 degree higher, will be polynomial. So quadratic is polynomial degree 2. Then the displacement function will be polynomial of degree 3. So A, find the displacement of the particle during the time period from 1 to 4. So t is from 1 to 4. So we want to find the area of S, right, from 1 to 4. So what's that? So we have, so by equation, the displacement is S of 4 minus S of 1. So what's S of 4? What's S of 1? So we can antiderivative, we can find the integral of V of t. So that is V of t integral from 1 to 4. From 1 to 4. So V of t is t squared minus t minus 6. Antiderivative of this, we get 1/3 of t cubed minus half of t squared minus 6t. Then we evaluate at the lower limit 1, upper limit 4. After evaluation, we get negative 9/2. All right, so the area above x-axis is smaller than the area below x-axis. That's what negative means. Right? So this means the particle's position at time t equals 4 is 4.5 meters to the left of its position at the start of the time period. Right? So the left in this application has a meaning. Okay. So B, find the distance traveled during this time period. So we can factor this velocity function. We can factor as t minus 3, t plus 2. Then, so velocity is less than or 0 in the interval of 1 to 3. It's bigger than 0 or equal to 0 on 3 to 4, right? Because we have this interval from 1 to 4 to consider. From 1 to 4 to consider. Then we see this is how the velocity function behaves. So it decreases, it's a negative in the interval 1 to 3, is positive on the interval of 3 to 4. Then the distance traveled is absolute value, all right? Absolute value of velocity is called speed. Okay, absolute value of velocity from 1 to 4. Then how do we do absolute value? So we have to take a part, we can only take a positive functions, right? That means this one cannot be negative. So what do? We know that it's a negative from 1 to 3. It's a positive from 3 to 4. So we split into two intervals. So from 1 to 3, because v of t is negative, we take an absolute value. So we have to have negative of the negative. From 3 to 4 is positive. So we evaluate this piece. We evaluate this piece because both pieces are positive. Now we can add them. So we get 61/6. Right, that's how we use in applications. Let's see more. Oh, there's no more. Okay, basically just using antiderivative skills. All right, let's try a couple. Okay, let's try from here. Let's see. Okay, all those good to good. So let's try up to 9. So 1 to 9. All right, so antiderivative, right? Antiderivative each term, then evaluate at the upper limit, subtract the evaluation at the lower limit. All right, let's try this couple. So 1 to 9, all right? Okay, we're missing a lot of people. And also, some of you here, oh, hold on. This is here. Some of you need to present, so you can get a presentation credits. Yeah, see, some of you are here, you don't have enough presentation to to get your presentation credits. So I would like to encourage you to do that. Okay, if anyone wants to show, you can claim the number on the chat. This should be very simple, right? The idea. Because we know how to take a derivative, then we just antiderivative. Right? If you are not sure, we can go back to check. Then we just evaluate at the top limit, evaluate at the lower limit, and we subtract them. Okay, let's see. So we start with 1. Malika wants to 1. Let me make you presenters. Okay, Henan 2, Amir 9. Yeah, get yourself ready. Sure, Anastasia. Yeah, just whenever, because we are approaching the end of the semester. But we may not be able to present. We may not be able to have enough time for presentation. All right, get yourself ready. I made you presenters. If anyone's ready, let me put this. You can show us your work, or you can explain to us. Malika, are you talking? I cannot hear you yet.
No, I wasn't talking yet. Hello, I'm talking now. So
Okay.
for question 1, we have to find the integral, right? So what I did was first I found the antiderivative of each term. So by using the power rule for the first one, so x to the power of 2, the antiderivative will be 1 over 3 x to the power of 3, and then the antiderivative of 3 antiderivative of 3 will be 3x. And then that would be, so 1 over 3x to the power of 3 minus 3x. And then what I did was I substituted b for the first antiderivative and then subtracted that by the antiderivative of, so I subtracted that by the antiderivative of a, and then I got 9 minus 9 minus negative 8 over 3 plus 6. So I subtracted that by the definition, and then I got negative 10 over 3. That makes sense.
Right. Your steps are right. Your thinking are right. Just make sure you know the notations.
Yeah, because I was having trouble with the notations, yeah.
You cannot put the equal sign here, right? The integral, the definite integral is a number. It's a number. So this, you just mean, if you're treating the integrand as someone's derivative, right, f prime, then your antiderivative is this, is 1/3 of x cubed minus 3x, right on the side, right? Then these are equaling to each other.
Okay, I got it, yeah.
So the first equal sign does not make any sense.
Okay.
But I know what you mean. Okay, looks great. Thank you, Malika.
Thank you.
Okay, next one. Henry, we see your screen.
Oh yeah, I also make the same mistake as her before, so
So how would you, like, can you change it?
can I add stuff?
Well, you can tell me, I'll add for you.
Oh, you would put capital F of X for the first equal sign.
Right. Otherwise, that wouldn't make sense.
Yeah.
So
And
by writing this, you have to think this is your f prime. The integrand is your f prime.
okay.
Right?
So first I took the antiderivative of this whole thing, and I got x to the fourth minus x to the third plus x squared, and then the upper and the lower. So I plug in the number. So it'd be 2 to the fourth minus 2 to the third, subtracted to the 1 to the fourth, and you get 12 minus 1, and the answer is 11.
That's right. Yeah. Okay. Good. Looks good. Thank you, Henry. Okay. Next one. Let me make you guys presenters.
Oh, Professor, is it my turn yet, or?
Yeah, you can go ahead if you're ready. Share your screen.
All right, so I'm just gonna draw it again. It's easier for me. So we're given the question. So we're given here 4, 1, and then we have here 4 minus 6u over the square root of u. So first what I did was I tried to simplify the function. So we have 4 over the square root of u minus 6u over the square root of u. And then from here, I just wrote fractions. In the end, I'm going to put back in radical form. So I have 4u to the negative 1/2 minus 6u to the negative 1/2. And then from there, our f prime of x, or our antiderivative, is so 4 times u to the half over half, that's 8u to the half. And then we have here negative 6 times u to the half over half, that's negative 12u to the half. And then all we have to do from here is evaluate f of 4 minus f of 1. So we have here 8 times 4 to the half, that's 8 times 2, which is 16. And then we have here minus 12 times 4 to the half minus 12 times 2 is 24. So we know that f of 4 is negative 8. And then we just do the same for the other one. And we have here 8 minus 12, that's negative 4. So 8 minus negative 4, sorry. 8 minus negative 4 is 12. Yeah. All right.
Okay. All right. Thank you. You just remember to write du, all right? Because the sign with the du is a pair. Without du, it just doesn't make sense. All right. Thank you, Amir. Who's next one?
All right, Professor.
If anybody has any question, feel free to ask. So we did a 1, we did 9, we did 2. Alexandra, you want to do 4. Kaiser, you want to do 7. Andrew, you claim 5. So whoever is ready, share screen. All right, I see someone's screen here. 7. That's Kaiser's.
So I'm doing number 7. I have the integral from pi 0 to pi for sine theta plus cosine theta d theta. And we take the antiderivative of, when we take the antiderivative of sine, we get negative cosine. So that will equal negative 4 cosine theta. And then when we take the antiderivative cosine, that's sine, so we get plus 3 sine theta, and then we draw the bar, and we have to evaluate the function at the upper and lower limit. And when we do that, we get negative 4 cosine pi plus 3 sine pi minus 4 cosine 0 minus 3 sine 0. Then we get 4 plus 0 minus negative 4 plus 0, and that gives us 8.
That's it. Great. Thank you, Kaiser. Alexandra or Angel? Okay. Okay, I see the screen here. Number 4, Alexandra's.
Hello.
Yeah, I can hear you now.
Oh, hi. Okay. Could you see the picture
Yeah.
that I put? Okay. So we're given the integral from 0 to 3, and so what I first did was I found the antiderivative, which I labeled as capital F of W. So I knew that antiderivative of 1 is just W. Antiderivative of 6W squared is 2W cubed, and negative 10W to the fourth is negative 2W to the fifth. Then I had plugged in the first number, which was 3, and I had subtracted by plugging in the next number, which was 0. And after that, I simplified, and I ended up with 3 plus 2 times 27 minus 2 times 243 minus 0, and I ended up with negative 429.
Okay, looks good. All right, thank you. Alexandra, thank you. So who's the next one? Andrew, I think you are the last one. Okay, 5. Yeah, see your screen. Oh, it's gone. Can you share with us again?
Okay.
I saw it, but then it disappeared.
It's loading.
Mm. Okay, you came back.
Came back?
Yeah, I saw your screen now.
Oh yeah, I can see it too. Okay, so first, what I did is I simplified the derivative, and then I found it to be 8x cubed minus 12x squared plus 2x minus 3. And then I find the antiderivative of that to be 2x to the fourth power minus 4x cubed plus x squared minus 3x. And then to find the integral, it's f of x equals f of 2 minus f of 0. Oh,
You can,
did you draw that?
yeah, you can equal this too, right?
Yeah.
F of x is this, right? It doesn't make sense. You see f of x equals f of 2 minus f of 0.
So that's f prime of x.
Which one is f prime of this one? No. This is equals to, right? So this is your inside is your f prime of x. And then you find the antiderivative. Then you subtract those two. So this equals to this. You see that equals to. Also, that's too small to write. So this equals to this, to the arrow.
Mm-hmm.
Okay, so don't write f of x equals to this. That don't make sense, right?
Okay.
This is wrong. Okay.
So then I plug in 2 to the to 2x to the fourth minus 4x cubed plus x squared minus 3x, and I also did the same. I plug in 0 and then subtracted, and it equals to negative 2.
Okay, great. Yeah, good. That's just right. Just this equal sign is not right. And this, by the evaluation theorem, this integral equals to f of 2 minus f of 0. All right. Okay. Thank you, Angel. Let's see. Any? Okay. Anybody else? Okay, pretty good. All right. Let's see. Now I'm going to leave you some questions so you can try and show next time. Anybody has any question from the homework, from the online homework? Okay, so for next class, next class, 31, 32. But let me also choose a couple from the before. Choose 27. Be careful with 27. 27 is absolute function, right? You have to figure out intervals of increasing and decreasing. 29, 31, 32. 43. 43 is indefinite integrals, right? Indefinite integrals, we add c to the end. 45, 47, 48. Okay, I'll leave this couple. Let's see. Okay, so far, so up to this point, right? You know, as long as you know Riemann sum, you know the definition of integral, we don't really need the definition or theorem 4 to evaluate integrals, right? Usually, and we use this, if it's a definite integral, in the end, it's a number. If it's an indefinite integral, we add c to the antiderivative function. So we just use our antiderivative skill to antiderivative the integrand. Then we evaluate the antiderivative function at the top limit, subtract evaluation at the lower limit. So we use the evaluation theorem. So I'm leaving you 27, 29, 31, 32, 43, 45, 47, 48 for next class. All right, especially 31 and 32, right? You think about it, what's wrong? What's wrong with this equation? All right, remember when we talk about this area, is talking about a pure mathematical area. We have area above x-axis, we have area down below x-axis, right? So we have to be careful with the intervals. So think about 31, 32. And 27, 29 involves absolute value. Absolute value, we have to care about the intervals again. So we may have to split the interval into 2 intervals, or sometimes maybe 3 intervals. And I also left you some question with this indefinite integrals, right? Indefinite integrals, we add c to it. Indefinite integrals does not give us a value. We cannot evaluate, but we can antiderivative, then add c to the antiderivative function. All right, any questions? So next class, we're going to talk about fundamental theorem of calculus. Okay, super important. Super important. If you can go ahead, you have time to go ahead, you know, preview a little bit. Super important concept. Okay, anyone has any questions? If not, I see you. So have a good weekend. I see you next Monday. All right. Thank you. Thank you. Have